Hi, this is another video on electric fields. So this time we look at the relationship between potential and the field. Okay, so in other words, how V relates to E. An electric field is set up between two parallel plates separated by a distance x by applying a potential difference across the plates. Now, so if we have a distance x, we have a potential difference. The arrow here always points towards the higher potential, which is on the top, because remember that's positive, that's negative. And now if we're going to do everything with a positive test charge, okay, and we're going to move a positive charge from the negative plate up to the positive plate. So we've actually got to do some work on it to get it there. Okay, so the work done is equal to, so F equals EQ is the force on it, and work equals Fx, where x is the distance from one side to the other. So that makes work equal to EQX. Okay, so we also know that PD, potential difference, is equal to work per unit charge. So we could say that V equals EQX, which is our work, divided by Q, our charge, and that means we get V equals EX. Or, if you remember from last year, E equals V over D. Sorry, I probably should have used that space before, but going all down here, and then we write E equals V over D, what we had before. And so the alternative units is volts per meter. As example, a potential difference of 600 volts exists between two plates which are 5 cm apart. Neutrons released from the negative plate. Find. So in other words, we have got two plates, and we have a negative and a positive plate. An electron is released from here. Okay, it's going to fly up there. Now it's going to have work done on it. Okay, it's going to have work done on it. It's going to increase its kinetic energy, so it's having work done on it. It's gaining potential energy and is turning into kinetic energy. So, what's the electric field strength between the plates? Well, it's going to be E equals V over D, because we know voltage and we know the distance between them. What's the force the electron while it's in the field? Well, you could do F equals EQ, so you grab your answer from before and multiply it by 1.6 times 10 to the minus 19 for the electron. What's the work done by electron as it crosses the positive plate, or reaches the positive plate? Oh, there's a spelling mistake there too. Okay, so what's the work done? Well, you've got that formula from before. Okay, so remember, so we had work equals force times distance, but the force is EQ D, like that. Okay, so it could also be equal to that. Yeah, so you just substitute in essentially. But we also know that voltage is work over charge, so you could actually just go work equals V times Q. So it's going to be 600 times 1.6 times 10 to the minus 19. So there's quite a few ways of working that one out. The gain in kinetic energy electron, well, it's the work done. The velocity electrons arrives at the anode assuming its initial velocity was 0, so in other words, just EK is equal to half mv squared, which is equal to that work done from before. Now, the rate of change in potential is essentially the electric field strength, okay? So this is the vector representation of the electric field, and the rate of change of it is the size of it. Okay, so essentially we're saying that E equals the rate of changing the voltage with respect to the changing distance. Okay, and so where dV over dx is called the potential gradient. So looking at it in respect to moving along an electric field, so we've got an electric field here, higher V as you oppose the electric field. Okay, so the electric field going left to right there, the higher potential is on the left. So effectively, if we graphed V versus X, you'll get a changing voltage over the distance. Okay, in this case, if it's a straight line, well then you have a constant electric field. Okay, so if you can imagine two parallel plates going one from one side to the other, you have a constant change in voltage from one side to the other, so there must be a constant electric field. It does change depending on the object, okay, or depending on what the situation is. But you just look at how it changes over time. Okay, so what we're going to look at is due to a charge, what is the potential at that point there? Okay, so having this situation set up, we've got plus Q charge there. We've got a distance x, distance r, point P, and a small charge. Okay, so we're going to look at considering the electric field. You can see sort of just in the background here around this positive charge. Okay, and essentially looking at it around at these 2 points. So as the object, that charge, the small q, is brought from infinity to that point P, which was a certain distance away from that big charge. Okay, we want to look at how the work done, what is the work done when it's charged. Okay, so if you're looking at this thing here, we have a graph of force versus displacement or distance, and we're bringing it right into R. Okay, so in terms of calculus, well, we've got force versus distance, so the area under this line is your work done. Okay, so we're going to calculate the work done from infinity. So what we do, we look at how a small quantity of work is done and as it moves a small distance x towards P. Okay, so sorry, not very good at my sigma signs here. So we've got to integrate with respect to x in this case. And where is the x? Well, it's in the force formula. So if you don't really understand what we're doing here, it's probably not too essential. Okay. Okay, so we've got F dx, putting it in some values. So not values, sorry, so formulas. So QQ 4 pi epsilon naught x squared, and we're doing it with respect to x. So continuing, taking out the constant stuff, okay, 4 pi epsilon naught, and then just leaving in there behind the x stuff, okay, and then doing the integration. Oops. Oh, oops, I missed a step, sorry. Saying here, if you actually put those values in, you get 1 over r minus over infinity, okay, and essentially just left with this. Okay. But since V equals W over Q, then V equals FD over Q. So putting in all the stuff, you essentially get V equals Q over 4 pi epsilon naught R. Okay, very complicated way of getting that. Essentially, all you could think about, get rid of all this, get rid of all that. All you have to realise is that, hey, V equals W over Q, and W is force times distance over Q. Putting in our Coulomb's law for force, Q over 4 pi epsilon naught R squared times R, all divided by Q. And that will simplify then to make Q over 4 pi epsilon naught R. Which we write in here. Okay, so let's look at doing just a quick little example. Let's say we had two positive charges. Let's if I get a pen. So two positive charges. This one's 2 coulombs, that one's 2 coulombs. And let's say we had them at a distance in total, distance of 6 centimeters apart. And let's make that 2 centimeters and make that 4 centimeters. So what we want to know is both the V and the E at that point. Okay, so first step we might look at calculating the electric field strength. Okay, so electric field strength, what's that equal to? If you got it, it's Q over 4 pi epsilon naught R squared. Now what we're going to do is actually calculate the electric field strength at this position from that one and from that one. So there's going to be two values because they would differ slightly because of the R value. So let's try that. Okay, so putting in the values. So first one, we have 2 divided by, actually we'll put in 1 over 4 pi epsilon naught is actually equal to 8.99 times 10 to the 9. Okay, and divide that by R squared, so that would be 0.04 squared for the one on the left here. Oh, sorry, the right. And for the one on the left, it would be 2 times 8.99 times 10 to the 9 divided by 0.02 squared. So let's see what they equal. Okay, so what we get is these two values here. Okay, now what it's telling us is actually the electric field from this one is going this way, the electric field from this one is going this way. And in fact they actually work to oppose each other, the vectors. And so that means the resultant electric field will actually be the difference between the two. Okay, and it will be stronger coming from this way, so that will be the predominant one. So if we find the difference between the two, you get about 3.4 times 10 to the 13. Okay, so that's electric field. Now for the next one, we'll just remove some stuff. Sorry, I should pause it. Okay, so now we're looking at the potential. Okay, so the potential is going to be Q over 4 pi epsilon naught R. So for working out for both, you got 2 over 4 pi epsilon naught times, let's say 0.04, and the other one's going to be that, blah blah blah, times 0.02. And we'll get two values. Okay, so we've got our two values of the potential at that point. Now essentially what that means, remember voltage is work per unit charge. So to get to this point here, so you say we're coming from infinity, okay, as per Buzz Lightyear, infinity and beyond. So coming in from infinity towards that one there, and okay, let's say we go through this point. You're doing work to get there. Okay, you actually have to push a positive charge against that field to get there. Now, if you think about it, then you're actually pushing against two of these charges, and so the voltage will actually increase because of that. So the total voltage at that point is the two of these added together. Okay. There's a very big voltage, it's mainly because it's a very big charge.